Now let's look at how we can calculate probabilities in the special case where we have equally likely outcomes. And then we'll also define what's called the inclusion-exclusion principle, which is helpful when calculating probabilities involving unions of events. So, equally likely outcomes. What we mean here, first, let's think about some examples of sample spaces. So some sample spaces, especially ones we'll use for our basic examples in this class, do have what are called equally likely outcomes, which means flipping a coin, I have equally likely heads versus tails. Flipping two coins, this idea of heads heads versus heads tails versus tails heads or tails tails, those are all equally likely. And so in this case, the probability of equally likely outcomes we define as just being the number of outcomes in the event divided by the number of outcomes in your sample space. So this is intuitive when we're thinking of probabilities because it's the fraction of ways that this could occur. Let's go back to the example that we started with in the previous video, which is rolling a fair six-sided die. We defined an event as rolling a multiple of 3. And so now we can see, in terms of how we would define the probability, I'm going to think of this as the number of outcomes in A, number of outcomes in that set, out of total number of outcomes of rolling a die. In S, well, there are two ways that I could get a multiple of 6. It's either a 3 or a 6. Total number of outcomes was 6, so this ends up being 1/3. So if that was your intuition at the beginning of the last video, yes, great job. You have good intuition for how we can calculate probabilities in these equally likely outcome situations. Let's take this idea now, try B and C. So take a second, see what you get. All right, so if I think of my event space here for event B, there's only one way I can roll a 5. So probability of B, number of ways that this can happen, I'm going to write it again as the number of outcomes in B out of the total number of outcomes, 1/6. And then probability of rolling an even number. So now I have 2, 4, 6. There's 3 ways that could happen. So that's going to be 3 out of 6, or 1/2. So that's intuitive with our understanding with die. I'm pointing it out in this basic example is because you're really going to have to be doing some counting. In this case, it was quick because I could list out the whole sample space, no problem. But we're going to see in future videos where sometimes listing all the options is way too cumbersome. And we're going to need to use some counting techniques, such as combinations or permutations, to help us get what's in the numerator and what's in the denominator when calculating probabilities. Now, what about if I want to do union? So what if I have A or B, the probability of A or B? And so again, now I'm looking at, that's now the probability, well, that's now the number of ways that I could get A or B. And so in other words, it's saying the number of elements in that set divided by the total number of elements in my sample space. And so here I have 6 elements in my sample space. The number of ways I could get A or B, I have 3, 6, or 5, so that's 3 total. Okay, that's one way to think of it. You can also notice that, wait, because these are mutually exclusive, by our third axiom of probability, this should be the sum of the individual probabilities. And we calculated those individual probabilities already. We had it was 2 out of 6 for A, and then 1 out of 6 for B, which gets me to the same spot. So, pointing this out because sometimes this counting way is fast, other times we're going to actually need some nice rules like this that will be much easier to use. Now, what is probability of A or C? So again, we can do it using the definition of equally likely outcomes by counting. So this one's 2, 4, 6. And if I look at it in terms of number of events, I'm going to say, well, number of outcomes. I'll say how many outcomes are in A or C out of the total number sample size. total of my sample space. So the denominator here is 6, and then A or C would be, I can either get 2, 3, 4, or 6. So there's going to be 4 options, so I would assume 2/3. That's one way I can do it. And now I want to see what breaks down, because what if I decide to say, okay, well, it's in a union, so can't I just add them? Probability of A plus probability of C. If I do that, I get 2/6, and then if we remember, my probability of C was 3/6, and all of a sudden I'm not getting the right answer. I'm getting 5/6 instead of 4/6. Something's wrong. Okay, and that is that our axiom about the union of these, the probability of the unions being the sum of the probabilities, only worked when A and B were disjoint or mutually exclusive, right? Because A and B are mutually exclusive. But A and C are not mutually exclusive. They actually contain an overlap. They both have the element 6. And so we need a new rule, or basically an update to this, that takes into account what happens if they're not mutually exclusive. And that leads us to what's called the inclusion-exclusion principle. So what is it? If I want any two events, the probability of E or F is going to be the sum of the probabilities, and then minus the probability of E and F. So it's basically a little update to what we started with. And so if we come back to here, we can now see why this is going to work. So now I'm going to get probability of A plus probability of C minus the intersection. And so that's why here we had originally 2/6, originally 3/6, and now I have to think of their intersection. 2, 4, 6, the probability of the intersection, there was only one where they intersected, or one element in their intersection. And so that gets me back to 4/6, which is what we had when we did it using equally likely outcome counting. So just a reminder, and keep this in mind, in general, this is always true. And in the case where they're mutually exclusive, so if they're mutually exclusive, let's put it that way. If this is empty, then the probability of the intersection just ends up being 0. And so that's how you get back to just the sum of the original ones when you have mutually exclusive events. Let's try one more practice. All right, so I tell you the probability that a student programs in Python is 28%. The probability the student programs in C++ is 7%. The probability the student programs in Python and C++ is 5%. What is the probability the student does not program in Python or C++? Go ahead, put this on pause and see what you can do. All right, so let's define Y as being the event that the student programs in Python. I'm just using Y instead of P because I'm going to be using P for probabilities. Let's do D for the student codes in C++. And again, I'm not using C because we might use C for complements. So just keeping in mind what variables we might need. All right, so those are my two events. And then I want to think about the known probabilities. So I do know the probability of Y is 0.28. I know the probability of D is 0.07. I know the probability of their intersection, Y and D, is 0.05. And then I want to think about what is it that I actually need to calculate. And so what we want here is the probability the student does not program in Python or C. Okay, let's do this in 2 steps. If we want to look at they program in Python or C, it would be that. But I want not that, so I want the complement. So that's what I'm looking for. And so how can I get that given the information I have? So one thing I can notice, a complement, the probability of a complement is the same as 1 minus the probability of the original. So this is 1 minus probability of this. Okay. And then I can think of, oh wait, I know how to do unions, right? So I'm going to have 1 minus the probability of that. And then this probability, all right, this is the probability of y plus the probability of d minus their intersection from that inclusion-exclusion property. Okay, there we go. And this is going to lead me to 1 minus, and then I have 0.28 plus 0.07 minus 0.05. At the end of the day, once you simplify, we're going to end up with 70%. So that's combining both ideas.